Welcome to screencast number 3 for Unit 4, Lesson 1. I'm on page 182, and I'm looking at the blue heading that says, what is the relationship between velocity and acceleration? All right. If you go back and think about vector quantities, we have talked about vector quantities being something that you can't completely describe with just a number. You have to also have a direction. So like velocity, acceleration is a vector quantity. It has both a size, okay, and a direction. Acceleration is a change in velocity. When velocity is not changing, acceleration is 0. A car, for instance, driving down a hill at constant speed and direction has no acceleration. The car does have acceleration if it speeds up, slows down, or if it turns to go around a hill, around a corner or something like that. On a graph of velocity versus time, acceleration is shown by movement up or down. So you're going to get to the do the math problem on page 183, and you'll notice that it's a little bit different than the graph that we did a couple of pages ago, because the title of this graph on page 183 is velocity versus time. And a couple of pages ago, we had one that was distance versus time. And the one from distance versus time, remember, it's distance divided by time that gives you speed. And here on page 183, velocity divided by time gives you acceleration. All right, so if you look back on page 182, I've written it in red. Acceleration equals a change in velocity divided by a change in time. Remember, the little triangles just means the words change in. And since velocity is measured in meters per second and time is measured in seconds, then you wind up with units of meters per second, or sometimes people say meters per second squared. That's your acceleration unit. Okay. Reminder that acceleration can be an increase in velocity, meaning that you're speeding up. If the velocity of an object and its acceleration are in the same direction, then the velocity increases. I drew a little picture for you. Remember, we often use arrows to represent vector quantities. So I drew a little truck and we hit the gas. We're going 25 meters per second, but when we hit the gas, we start to accelerate, and so we speed up. You notice that the arrow for velocity is pointed to the right, the arrow for acceleration is pointed to the right. And so because the acceleration and the velocity are oriented in the same direction, that's going to cause the car to speed up, or the truck to speed up. All right, next red heading says acceleration can be a decrease in velocity, meaning that it can be something that's slowing down. Sometimes people say deceleration. Sometimes people say negative acceleration. Okay? So acceleration can be speeding up or slowing down. If velocity and acceleration are in opposite directions, then the speed is decreasing. Look at the second example of the truck. If you are moving forward at 25 meters per second and you hit the brakes, y'all know that the truck is still moving forward, but it's slowing down a bunch because the acceleration is oriented to the left, whereas the velocity was oriented to the right. They're working against each other, so the truck is being slowed down. I put, again, a little note to remind you that acceleration is something you can feel. When you get in a car and somebody speeds up, you feel pushed back into the seat that's supporting your back. When somebody slams on the brakes, you tend to lurch forward until your seatbelt catches you. When you whip around a corner, you tend to lurch to one side or the other depending on which way you're turning. So acceleration is something that you can feel. Look at page 183 at the third red heading that says acceleration can be a change in direction. Now, if something is accelerating simply because it's changing direction, we don't really do a calculation to indicate that like we would if it was speeding up or slowing down, but it's still accelerating. All right? So a change in direction is also considered acceleration. For instance, if you take an object moving around and around a circular track, their speed may be the same the entire time they're moving, but they're constantly accelerating because they're constantly changing direction. Okay, there has to be some sort of force there to allow them to be constantly changing direction. And for instance, if it was a car, it would be, for instance, the friction of the tires against the road allowing you to do that. Planets that orbit the sun are doing the same thing because it's circular motion. Circular motion requires a force because the object is constantly accelerating, because the object is constantly changing direction. It may not seem like it's accelerating to you because the speed's not changing. But remember, please, that acceleration is speeding up, slowing down, or changing direction. And if you're being moved in a circle, you're constantly changing direction. All right, look down a little bit. I'm still on page 183. I'm on the second paragraph. Average acceleration is equal to the change in velocity divided by the time over which that change occurs. And then they give you a formula. Average acceleration equals final velocity minus starting velocity. You'll hear me call that initial velocity. Okay, initial just is another word for starting. So basically what you've got on the top is the change in velocity, and on the bottom you have the change in time. Acceleration can also be represented by the slope of a velocity versus time graph. That's really important. Okay? The slope of a distance versus time graph, you remember a couple of pages ago, was speed, or if direction was implied, it would be velocity. But the slope of a velocity versus time graph tells you acceleration. Okay? One thing I want to point out, and we will mention this several times before the end of this unit, a lot of people tend to automatically say or assume, sort of without thinking, that if an object's not accelerating, then it's not moving. And please understand that there's a difference between an object moving and an object accelerating. If an object is accelerating, then it's changing the way it's moving. And the only way it can change the way it's moving is by a force acting on it. You can still be in motion at constant velocity. Okay? So if there's no acceleration, that just means you can't be changing the way you're moving. You can still be moving, but you just can't be changing how you're moving if you're not accelerating. All right. So I'm going to break off and do the math problem on page 183 in a separate screencast because I'm going to cover that, and then there's another one as part of your lesson review that we'll walk through together also.